So this is going to be the 3D printing session. When I put this stuff together, I was told this is going to be an hour-long session, and it's only a half hour, so we're going to go through it pretty quickly. But if you have questions and I'm talking fast, just talk faster and louder than me, and I will start listening to you. That will work. I would love it for it to be a discussion, and I'm here to answer your guys' questions more than just to talk to you. So if you have questions, definitely go ahead and ask them. So what 3D printing is, who in this room has interacted with a 3D printer? You own one, you use one, you've had parts printed. Maybe I should ask who hasn't, who's totally new to 3D printing. That's awesome. So when I started working with the 3D printing about 3 years ago, it was new to almost everybody. And now it's not new to everybody, it's becoming more commonplace, and what's actually becoming really rare is somebody who hasn't used it or hasn't interacted. Even my grandparents, I think, have used 3D printers. My grandpa, for sure, he's more technically savvy than I am. So you guys are probably aware of this. One of the main differences about 3D printing as a manufacturing technology is that it's additive as opposed to subtractive like machining. And because it's additive, and because the parts are built from the bottom up, it opens you up to different geometries and different shapes that you can create without any downsides. When it comes to creating a shape like that chassis, if you're going to mold it or if you're going to machine it, the costs go up with complexity. Whereas 3D printing, the cost stays flat. It's just based on basically the volume and time to print, most likely. So you get the complexity for free. Everything's done digitally. We work from 3D CAD files, typically STL files. And there's no drawings involved with 3D printing. And it's super accessible. Like I said, my grandparents have used printers. If you can print a birthday card, you can 3D print a part. And I can teach anybody how to use the software that controls this printer very quickly. If you sat in during the CAM software session I did earlier, it might take me a day, 2, 3, 4, 5 days to teach you how to CNC program a part. Whereas these chassis, which are extremely complex, you can come in and you can print it within a couple minutes, just learning how to use the software. It's also more accessible in that the machine, a lot of the technologies are becoming more office friendly. Like I could have a printer in here running as we speak, and you don't have the same facility needs that you would have with more conventional manufacturing. So there's a lot of different types of 3D printing. 3D printing is sort of this very broad, generalized term, and it's becoming even more generalized as more and more people start learning how to 3D print things like concrete and cake frosting. Full-on concrete, yeah, and they grind up stones and mix it, and it's concrete. I think in Dubai, Dubai just opened up an office building that was 3D printed. Amazing. Just imagine a giant XYZ, system. So there's lots of different methods, and they all like to come up with their own name. The two technologies that we represent here at Go, because we're partnered with a company called Stratasys, are FDM and PolyJet. These are going to be the two technologies that we cover today. So FDM, it stands for Fused Deposition Modeling. It's actually probably the most common 3D printing technology out there, especially on the hobbyist level. These are the machines that are the most accessible. They're the least technically advanced, but they offer a pretty wide range of materials, all thermoplastic materials. Okay, so things like ABS, polycarbonate, nylon, Ultem, PPSF, ASA, all sorts of stuff. These parts are typically used for more industrial purposes, things like jigs, fixtures, tooling, also a lot of functional prototyping as well. And this technology is definitely office friendly. It's all self-contained. You guys might have seen some machines in there. The big machine as you walk right in is a big FDM machine. It's all standalone stuff. I am going to play this video. It's a quick overview of FDM, and I'm not plugged into any speakers, but I'm pretty sure this will still be loud enough.
Fused deposition modeling is a 3D printing method that makes durable objects out of the same plastics you see in everyday products. With FDM, the 3D printer takes a spool of plastic filament, melts it, and extrudes it onto a tray to build a part layer by layer from the bottom up. FDM materials are all industrial-grade thermoplastics, That's what makes the resulting parts so tough. And it's also why FDM is changing the way industries design and manufacture. With FDM, a designer can sketch an idea and test it the same day. Industries can cut lead times and costs. Products turn out better and get to market faster. FDM parts are helping to build the cars you drive. They're in the airplanes you fly in. They're in the medical devices that save lives. FDM is cutting waste in manufacturing. It's helping engineers power remote villages in Africa. It's helping farmers feed an ever-expanding population. And the ideas keep coming.
I love just having videos. It makes my job so much easier. It's like, watch this video. It's like in school when they roll in the TV. You're like, oh, yes. Everybody loves to just sit back and watch a video. So PolyJet, that's the second type of technology that we have through Stratasys. It's very different, but I think it's very complementary to FDM. Everything's resin-based. So instead of having this filament of thermoplastic, you have a jar of resin. It's all liquid. They're all acrylic or methacrylate based, and then they have different additives. And those additives give it different properties. It can make it rigid or flexible. It can make it opaque or clear. You could do grayscale or even full spectrum color. Okay. You can do multi-material printing. So within this model, this is all printed at one time. You have different materials embedded in others. You have some materials that have been mixed together, especially when it comes to color. You might load cyan, yellow, magenta, and you can reach a whole spectrum of different colors. The layering on this, so most all 3D printing is done by layer. These layers are a lot finer than you would see in FDM. Okay? So they're about an order of a magnitude smaller. So here's an FDM part. When you look at it, you'll be able to see the layers. The more shallow a surface is, the more evident layers are. So this is printed at, this is pretty coarse, this is probably 13 thousandths of an inch. It's the most coarse you can run it. And then on PolyJet, the layers are more like 5-10 thousandths of an inch. So you get better surface finish and higher detail.
PolyJet is a 3D printing method that makes beautiful, precise models in a huge variety of materials and colors. It works like an inkjet printer, but instead of jetting drops of ink, PolyJet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts. Soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
I know what's next, because they made that video a while back and they came out with a new machine called the J750, which I was talking to one person about. I don't think I have anything about that in here, but this image came off the J750. So the old machine, the Connex, the old flagship PolyJet machine was called the Connex 3. You could load up 3 different materials, mix them together, etc. This J750, you can load up 6 materials and mix up to 6 like colors or clears or rigid or opaque or rubbers, all sorts of different things. And you can also read in a full color map. So you could read in like a file with 3D CAD and then also a wrapped JPEG or bitmap image. So you can get all sorts of cool stuff. Talking about the materials real quick. FDM, like I said, it's all thermoplastics, whereas the PolyJet's all thermoset materials. That right away is going to dictate a lot of the usage of these printers. We have ABS family. Depending on your machine, you get different blends of ABS. Also, on the higher end machines, you get the option of an electrostatic dissipative ABS material. ASA, which is replacing a lot of the basic prototyping that we used to do in ABS, we now do it in ASA. Very similar styrene-based material. Polycarbonate, we have an ISO certified polycarbonate for medical grade accountability issues and stuff like that. And then we have a PCABS blend. We have nylon 12 right now. We have something called Ultem. We have two blends, 9085 and 1010. These are basically the flagship materials on the FDM machines. They're highest heat, highest strength, highest rigidity materials. They are very chemically resistant, and they hold different certifications. 9085 is FAA certifiable for flight. So when you read about companies like Airbus using 3D printed components on their new aircraft, a lot of those are metal, but a lot of those are plastic. And a lot of times when they're plastic, it's going to be the most popular option, Ultem material. The 1010 is the highest heat. It can be used under load up around 400 degrees Fahrenheit. And then our most chemically resistant material would be our PPSF. On the PolyJet side, they're all photopolymers, they're all UV cured, and they're all acrylic based, like I mentioned. So the differences are more qualitative. So we have a rigid opaque group. These would be just basic materials that are rigid and opaque. We have a transparent group. We also have medical grade materials. So these are our biocompatible materials. They hold certifications for contact with the human skin, contact with mucous membranes for a certain amount of time, stuff like that. Also a whole line of dental materials. Some simulated materials, simulated polypropylene. So these are more prototyping materials that we need a little bit more flexibility than what you would get in the more rigid PolyJet materials. Some simulated rubbers. Okay, so of different Shore A values, anywhere from Shore A 27 to about Shore A 95. And then we have a whole category called digital materials. Digital materials are the mixing of these materials prior to curing. So they're mixed in certain ratios and then cured, and that will give them certain attributes. So one we call digital ABS. It's like an ABS-like material. It's what's used for tooling most often when you go with PolyJet. So things like 3D printed injection mold inserts. We can target different durometers when it comes to the rubber-like. So if I'm simulating a gasket and I need it to be Shore 60, I can hit that by mixing a little bit of rigid and a little bit of rubber-like material. And then also a full color palette. So actually with the J750, we get about 360,000 different colors. You basically just can pick RGB values and it applies it. You can also put like a texture. I did some carbon fiber pieces. If I didn't want to actually go through the process of creating a carbon fiber piece, and just pull my CAD file into Photoshop, apply a carbon fiber texture on it, and then output that, and the J750 will print it. So I like to say you can simulate almost anything. When it comes to 3D printing industries, obviously we're in a lot of different industries. It's exciting to be able to work with some of the industries that we typically don't get to work with in the SolidWorks lineup. But aerospace and medical and automotive are our big three. And part of that is because we have certified materials for those guys, those industries. So let's get into some applications. Prototyping is still the number one application for 3D printing. I read a study that said over 60% of parts that are printed are still prototype parts. But digital manufacturing applications are growing. Things like the urethane casting and the injection mold inserts, sand casting patterns, stuff like that. And then also marketing models. Just creating models for marketing purposes, things that need to look good and look realistic even if the actual product doesn't exist at all. So a good example of a prototype would be the car that you've seen several times today. This one's all printed in FDM primarily. The printing workflow looks something like this. It's 3 easy steps. The CAD file, then you output an STL, or if you're using the J750, it would be a different file format. You process it, which basically means you take the model, you orient it, you tell it to slice it up. You might choose a slice height, and you tell it to print. Processing is super easy. Print it, send it to the job. Okay, so this is our chassis. Did you guys sit through the Inspire stuff? Inspire, you like that? Yeah, so I did this in Inspire. Jeff took credit, he didn't do it. Oh, there wasn't. But that's all different. That's a change in material. Like if I designed this with plastic in mind, and we're comparing 3D printed plastic versus injection molded filled nylon, so it's very hard for me to use less material. I was working with a company called Concept Laser. I thought I had them on board to print that, and if I would have, he talked about load pass, I'm sure. Inspire comes up with a load pass. I could have made these a lot thinner, and then I would have saved money. But because I downgraded materials, I didn't save anyway. Okay. So this is a screenshot from Insight. So this is the software that processes the FDM stuff. What you're looking at is a slice at a time. So I'm going up and down the model, and you're just looking at a screen grab. So what you're seeing here is in thicker parts, it's actually pretty more sparse. And as it's approaching a visible surface, or as the surfaces get, the internal voids get smaller, it starts to print more solid here. And so we can do that with FDM because it's all self-supporting. We can have an internal lattice structure inside of it. Our CAD file doesn't have to have that. We just choose the internal fill, sparse fill. On PolyJet, it can't self-support, so it's completely solid no matter what. So you can see I oriented it in this way. Any ideas why I might have oriented it in this way? So it's printed on its side. The one I passed out, the one I passed around, was printed like this. This guy was printed like this. Why do you think the difference? Yeah, strength is a big one. That's a big one too. Yep, more support would be more time and more cost and more cost. Aesthetics is another one. The layers are really evident on this one, right? Whereas on this one, since more of our walls are more vertical, the aesthetics is a little bit better. On the top edges, it's not as good. So there's a few different reasons why I chose this. Mostly it's aesthetics, but also strength. These two, I knew this model was weakest like this, bending, right? Because of this huge gap here. What I would really want to avoid is printing it in such a way, like printing it this way, up and down. Because then my layers would be here, and I'd have tons of little shear planes in my model. If that's the weakest spot, then I just made it. Right? If I print it like this, or even like this, in bending, it's a lot stronger. So orienting your model is actually probably one of the toughest decisions you have to make with FDM, which is kind of saying a lot for how simple it is. So here's that particular black one printed. It's still in the machine. We printed it on the Fortis 400. This was PC ABS. It wasn't my first choice of material, but it's what was loaded up in there, and I didn't want to unload it. And it's a good enough material for a prototype, so that's what I chose. You can see all of the support material that was created. The support material is there to support overhangs, right? Because we're printing layer by layer. When you go to lay down some material, it has to rest on something. This is all root beer colored. It's all water soluble. So we put that in our ultrasonic tank and it dissolves away. Normally I'll break away as much of it as I can. I won't spend longer than a minute or so, but a minute of breaking it away can save maybe an hour of time in the ultrasonic bath. There it is in the ultrasonic bath. Awesome. Overall, that was probably in the bath for a couple hours. So it takes a little bit longer than PolyJet, which is more hands-on. So there's a trade-off there. This is hands-off. That ultrasonic bath is basically just water with a little bit of sodium hydroxide. So now there's a couple things that we can do with FDM. I knew it was weakest in this area, and I wanted to do something about it. So in a different chassis, I created some little internal voids in here. And I bought some carbon fiber sticks off Amazon. And what I did was, within Insight, when I got to this layer, I programmed a pause in there. So the machine pauses, you go open the door, you put your little carbon fiber stick, or it could be metal rod, or it could be magnets, or RFID tags, or all sorts of stuff. Insert it. As long as it's not poking out above the current layer, you're good. So you just keep printing over it. Okay? Yeah. Uprint and Catalyst do not. Oh, yeah, they do. Catalyst will allow you to pause it. Yeah. You basically just browse to the layer that you want it to pause prior to printing, and then there's just a little drop down, insert pause. right? So you pause it, and then it had actually 2 pauses in there. So that gives it a little bit extra stiffness. There's some pretty creative things that you can start to do with the printed stuff that goes beyond just the actual printing. You guys might have noticed, like in this model, there's a lot of little brass inserts, little threaded inserts. I like to use these anytime I'm going to, repeatedly screw in and screw out an insert or screw, because it doesn't degrade over time and it's a lot stronger, right? We can print threads, and I've done tests. I can print threads down to a size 6, like a 632 size screw, but they're not very strong. They're not very accurate. So in SolidWorks, I just have this little library feature. It's a little tapered hole that's sized correctly for these tapered inserts, and I pop them in with a soldering iron. They just heat up, melts the plastic a little bit, it's interference fit. You pull the soldering iron off, the plastic cools, and these inserts are in there for good. Okay. When I didn't have enough room for the inserts, then it comes to threading. Threading is preferred over printing, but again, it's still a plastic thread, so it's not ideal. Another thing I did on these control arms, a nice little trick if you guys have FDM printers, is something like a solvent-based plastic weld. In some of these areas that were really small, that was an M3 tap, so it's pretty small. Just this really thin weld, plastic weld, paint over top of it, it sort of sucks down into the part, capillary action into it, and makes it a little bit solid, more solid. Nice little strength feature for small features. The rear wing, he might have talked about this in Inspire, did he? So I did a printed version. I also did a carbon fiber version. In the printed version, we printed standing up. And again, it came down to aesthetics. You can imagine if we printed this sitting flat, you'd have lots of shallow surfaces, right? So those discrete layers would be jumping up 10, 13 thousandths at a time. If I went as fine as possible, I can do 5 thousandths. But if you stand it upright, all of those layers, all of those walls now become mostly vertical, and you see almost no evidence. So another thing that I did, if you guys have FDM printers and you're using Insight software, is you can convert support material over to model material. So that's what this little guy is here. It needed support material for this geometry up here. And the way it works is it can only lay down one material at a time. And it does it every 2 layers. So you'll lay down 2 layers of model, does tip change, come down, lay down 2 layers of support. Does that every 2 layers. So over hundreds of layers, that time starts to add up. So within the software, you can actually say, hey, because these 2 aren't actually touching, just make them both model material, and then just break it off. And I save 100 tip changes. I think that took it from a 12-hour print to an 8-hour print. The material cost is the same, so nice little trick. Yeah, these are model, and then the layers that are still interfacing with the part, like these guys here, they're still support. No, support is less expensive. Then it's the same price as ABS, but if you're using something like polycarbonate and nylon, it's less expensive. So there's a little bit extra cost if you were to do that. I'm changing the support to model. On the wheels, we printed these on PolyJet. The reason why I did them on PolyJet is we had thinner walls, thinner features, definitely a better fit for PolyJet. Another thing that I wanted to do was I wanted to print different shore values within the same model. I wanted the center hub to be very rigid, so I printed it shore D85. And then in the middle, I targeted a shore A65, and then on the outer side, shore A45. So I can just, in SolidWorks, I just created 3 separate bodies, boom, boom, boom. And then in the software, in PolyJet Studio, you just assign different materials to different bodies. What's cool on the J750, if we had one, which hopefully we will in the next month or so, I actually could have got this texture from SolidWorks. I could have printed that texture out. And I could have got my green, which I couldn't do. Yeah, so those are all done at one print on the same time. Gearbox was another one. The printed one I had broke. I actually had to rebuild that whole car again last night. Because we did this event in in Northern California last week, and then they shipped me a broken car without telling me. So I opened it up yesterday. I was like, oh, okay, this is cool. Okay. But actually, how many times have you guys had prototypes break right before you had an important meeting, right? Or parts break? I replaced that whole car in 24 hours. So, I mean, you couldn't do that with any other manufacturing technology, I don't think. You can see this was done in matte finish, and that's why you have that support material all around. Okay, on the PolyJet side, the support material is like almost jelly-like material, and we spray it off with a we call it a water jet, but it's not really what I would consider a water jet. It's a pressure washer. You can see I chose PolyJet for the gearboxes because they have pressed bearings, and the one that I did in Panic yesterday is actually FDM, just because I only had an FDM machine open. And it was a lot harder for me to get these bearings in there, because on FDM, anytime you have an internal thing here, a lot of times you have something called a seam, which takes that out of tolerance a little bit, because it has to move from one layer to the next, and you get a little nub. And so on the FDM, I pushed them in as far as I could, and then I used my soldering iron to push them in the rest of the way. The soldering iron, it doesn't solder a lot of stuff. It just pushes stuff into things. All right, another thing we did was a carbon fiber skid plate. This is attached to the car out in the front. Using 3D printing for carbon fiber layup is an awesomely synergistic use of 3D printing, because the hardest part in this process, a lot of times, is just creating the shape to lay the carbon fiber over. So you just design a guy like this. This is printed in ABS, and it's printed in spar, so it's very light. It is up here. Another thing I did was something called an intensifier. And this is just a little extra piece that, I might not have done if it was not very cost effective to create these shapes. But you guys can see its intent. Basically, the carbon fiber gets laid up over this, but I needed to press it down into here. And I was concerned about my vacuum bag not really doing that. So you put this between the vacuum bag and the carbon fiber, so it presses it down. We call those intensifiers. That's also made out of ABS. This vacuum bag, I don't have an autoclave set up in my garage, so I decided to do a wet layup. But a lot of our materials will withstand the pressure and temperature of an autoclave. You might not be able to use ABS, but you might need to go up to something like this. That's it, just pretty much fresh. And then I'll trim the size. I just use the intensifier to trim it to size. So you just clamp it on and just run it over the floor. That's an example of a template or a camera. I should probably explain that a little bit more. So I lay down dry sheets of carbon fiber, and then I have a 2-part epoxy that I use a paintbrush to paint on. And then I did, I think, 3 layers on this. It's pretty good. And then you cover the whole thing with a vacuum bag, full of vacuum, compresses it all together, and then wait a few hours. Another thing I wanted to do was a carbon fiber wing, because the wing was actually probably one of the most fragile pieces on that car. It seemed like every time I backed up into something, it would chip off. And so this was a pretty good opportunity to make a carbon fiber wing. I wanted to do something called a soluble core. We can print parts in the support material here on the inside. And actually, Stratasys just came out with a new material specifically targeted to do this sort of situation. One thing that I had issues with, because the wing doesn't have that support structure that the original wing did, it didn't really need any support. Okay, so if I stand it up like this, I was really concerned about it wobbling and waving as I printed it. It's pretty common. So within Insight, there's some tools that you can add things called stabilizer walls if you're concerned about that. So it's sort of like a scaffolding. You can actually see the printed model here. It's perforated. It only ties into the model every 10 layers or so. So I just peel this off and just run over the same thing. But it helps keep the model stable. It's one of the things I'm concerned about is being able to actually stand up. I also did something called a porous hexagonal fill. So this is a fill that's not really meant for strength. It's meant to allow fluid to flow through very efficiently because I was going to melt all this out. So this is all out of the soluble support material. I wrapped that in the carbon fiber, and you can see after it's cured it looks something like this. And then I stuck this whole thing in the ultrasonic tank, and it dissolved out. So this ends up being volatile. Or this would end up being, if it was just standard ABS that I used, it would be a trap form. So that's really common for things like carbon fiber ducting and motorsports, fiberglass ducting. Similar, yeah. Yep, you're melting out. It's a one-time use. Because if I just put this in the bath, I would have nothing to take out. It would just all dissolve. Oh, the whole thing was soluble. Yeah, this whole thing is soluble. All right, I wanted to do some urethane casting as well. I've been doing a lot of urethane casting. I like urethane because it's super versatile. You can buy it very soft and rubbery. You can buy it rock hard, filled, everything in between. And with the printers, I take care of the hardest part of the process. It's creating the shape of the mold. So I wanted to do some rear control arms. I printed a lot of different ones, and I haven't had one break, but I did feel like I could make a stronger one. So I printed on PolyJet some molds. You can see them here, and I'm not going to pass around because the urethane is kind of sticky. This is just Vero white, so it's the standard, like lowest of the low grade PolyJet material. But I did print this on high quality, which is about 5 to 10,000. So I get these guys out. Nothing too tricky about these molds. They just bolt together. There's some features that I might not have added otherwise. Something like this. I wanted to use these same inserts, but I wanted them to be embedded in the plastic. So just the same way you would do any sort of insert. This guy's in. This is a two-part process. So you mix up the plastic, you vacuum degas it, get all the bubbles out. And then I just use a syringe to push it through, and then you cure this under pressure. So I just put it in a paint pot. Don't go higher than that. You lie when you're dead. And then your wife will tell you, be careful, and then you'll get upset because you just had your death experience. Okay, so this is the result. And again, if you do want to come up and look at this, I'm not going to pass it around because it's a little greasy. It's still got some. But the result is actually very good. I didn't do any post-processing on these guys. Outside of cleaning the support material off, I didn't sand these, I didn't touch these. Spray foam grease on them, that's it. So there's no flashing, and you can even see very hard, but I had some vents on the end of this mold. You guys see those things hanging off? Those are 5,000ths. So that's the sort of resolution that we can get on here. No, I inserted them prior to. Oh, yeah, that's correct. So you'll see on this one, these don't have any holes. And I kind of did this last minute, which is probably a big surprise. But I wanted to get on McMaster and get some pins and use the pins in the mold and just slide them out. That would have been ideal. But now that you know I thought about it, it's just the same for me as if I had done it. Just some close-ups there. Another part that I thought would benefit from urethane casting, specifically soft, and I should say, I wanted to do this in hard, and I did it in soft because I ran out of parts. Whatever. But a soft, more durable urethane casting, because those PolyJet tires that I passed around, those aren't the most durable parts. You can even see that some of them are already deteriorating from people pressing on them a lot. And, it's because the walls are so thin, and that might not translate to being a problem. But, what if I kind of combine the best of both worlds? An FDM rim, and then a cast urethane outer portion. be a lot more durable, it'd be a pretty good product. So that's what I did. Basically, same thing. This is PolyJet on the mold, and then the interior was all FDM. You know what? I did, but it didn't work out very well. So you actually, if you notice, there's a difference between these two pictures. So what I originally did was I took the tire, I bolted it to the plate, I bolted everything to the plate, and I tried to cast it over mold. What ended up happening was the urethane just went underneath there. So I have on my desk a tread that's really this tall. So then I changed it. This one's all one piece. And you'll see. This comes off. This is a separate piece. Okay. And this looks like this. That's a separate piece. I mean, this stuff is... But same sort of process. It's actually the exact same process. And again, you see all of the detail, all of the features that you could want. So we almost made it through a half hour. Any questions about that? Yeah, it's hard to find locally. It's a product from a company called Smooth On. This one in particular is called Vitaflex, I think. They have a few, I mean, they have urethanes, they have rubbers, they have silicones, they have all sorts of casting things. I don't know anybody local. Do you know anybody local, Quentin? You know, Utrecht, there's an art supply store called Utrecht in Sugar House. They carry the filled urethane. It's called Smooth Cast. They carry one type of it, but it's the fast curing stuff. So, yeah. Yeah, they have Amazon, so they're good. The big point there is that I'm really on this mission to teach people that printing is more than just a prototyping tool. It is a great prototyping tool, but if you just keep it within that little niche, you're not really fully taking advantage of 3D printers as a tool that creates shapes. And you can do all sorts of stuff with shapes. Like Quentin was talking about using them for masking, chemical masking, paint masking. Audi, I know, does that. They create these nice 3D masking tools. Put it right up to the window, paint all around. It's really cool. If the hardest part in your thing is creating a shape, then printer might be a solution. So if you guys want these slides or if you guys have any questions, it's the end of the day. I'm going to be here for a little bit. You can shoot me an email or just answer the questions if you don't have any right now. Cool. Well, thank you guys for coming. And this is the last session. So thank you guys for sticking out the whole day. I appreciate that a lot. And hopefully you guys saw at least one thing that sort of piqued your interest or was new to you. Because I know we have so many products. We work with such good vendors and they come out with such great products that I wish I had the time to learn all of them, you know, and I wish I had a use for all of them. I don't, but we have a lot of great tools for almost everything. So thank you guys for coming.